Yes.
So, good afternoon, everyone. Today, the Adams Seminar has the great pleasure to welcome Professor Michael Schertz. Professor Schertz graduated from Harvard University in chemistry and afterward was at Stanford University receiving a PhD in chemistry. He was an NIH postdoctoral fellow at Columbia and then started as a faculty member at the University of Virginia in 2008. And in 2015, he moved to the University of Colorado Boulder, where he's currently an associate professor of chemical and biological engineering.
Well,
Prof-
that's out of date. I should update that somewhere. I'm a full professor now.
Oh, that's great. Professor Schertz
We'll
works to
talk
design and
afterwards to
character.
figure out where that's posted so we can fix that.
All right, all right. Professor Schertz works to design and characterize new molecules and materials at the nanoscale through the use of theory and computation. His focuses include the prediction of physical-chemical properties, protein ligand binding affinities, and properties of novel biomimetic materials. He's especially interested in the development of computational tools that can fundamentally change molecular design by making searches through chemical and configurational space much more predictive, reliable, and efficient. So once again, welcome, Professor Schertz. Thank you so much for being here with us, and please feel free to start your presentation.
Great. All right, I'll
Sure,
start
it's
in.
great.
Yes, it's great to be here virtually and talking to you all about some of the. This is a project I've been thinking about for a long time. I think Professor O'Connell might have remembered me talking about this when I first interviewed at UVA. And we've made some progress since then, although it's sort of been a different thing than a lot of people do. So which makes it exciting to me. So the idea is learning how to build molecules that fold like proteins. So I'll explain what that means. First, it's important to recognize the contributors. So Lenny Foba, graduate student in my group, recently graduated, and Chris Walker, and as well as Garrett Meeker, postdocs that have worked on this, and an undergraduate, Sarah Millett. But mostly Lenny and Chris drove this project, funded by the U.S. Department of Energy, and with some collaborators such as Sam Gelman at University of Wisconsin-Madison. So very important to recognize the people who did a lot of the work on the ground. So I'll mention a little bit more who did what as we go through. So what are foldamers? This isn't a concept that's come across. And these foldamers are biomimetic polymers that adopt stable three-dimensional structures in the same way that proteins do. Here's a couple of examples of ways that you can fold up into, in this case, secondary structure that is not actually what the proteins are doing. And if you think about it, if nature can do everything it does with just amino acids and nucleic acids, what else is possible with the entire chemical palette? All sorts of monomers that you can get. So what we want to know eventually is what are the rules governing the formation of such stable three-dimensional structures across all of organic chemistry? And then this really opens the doors for things like novel selective catalysts under extreme conditions, things that are stable under solvents, temperatures, or pressures that proteins are not. Self-assembled switchable materials in the same way you can form these sort of self-assembled materials with small peptides, can form certain aggregate structures, fibrils. You could do far more if you have all of chemistry around, and precisely organized electronically conductive structures. If you can, insert metals in there as well, you can make structures that are far more conductive. And if they can order them, then you can start looking at very complex functional structures. So this is the idea, is that, proteins, one backbone, 20 side chains, how boring when there's all of chemistry to play with. So that's what we ought to understand. And an issue is that it's incredibly slow to synthesize these non-biological polymers. So why would modeling computation be useful? There are a number of well-explored scaffolds already. People have been looking at, alpha peptides is what we usually see, but beta peptides, peptoids, people have been doing experiments with these. These are experimental structures of small beta peptide helices, if you get the right sequences, form stable structures. However, without nature to hijack to make new molecules. In proteins, we can just edit the DNA and have nature make the proteins for us. We don't have to synthesize them step by step. But without nature to do that, we're left with relatively slow step-by-step synthesis methods. For example, taking solid phase synthesis is the common way to do this. But there's a lot of trial and error involved because once you have different chemistries, you need different protective groups. You have to do all sorts of things differently. So and that process could be optimized if we know to make what to make, but how do we know what to make? That's the key. And this is where computation can be key in the design of foldamers, even more so than in peptides. With peptides and proteins, I mean, we've got AlphaFold. There's a lot of tools we have that can tell us what structures which proteins would have, but there isn't for foldamers. And this is why computation can provide a big advantage. So what can we do to do this? Well, let's take an example. So this is a collaboration with Sam Gelman. I don't know if you're familiar. He really coined the term foldamers in a seminal paper about 20 years ago, saying, hey, what are all these possibilities? And it's really his paper that inspired me. So we actually started working with them a couple years ago. They had a particular terphenyl oligomer. This is what the monomer looks like. And so those P's and O's, that's just saying that the substitutions at para, ortho, para. We'll see that again, this sort of nomenclature. So they were looking at these, and they found signs of helical behavior. So here's a circular dichroism. And so if you see a flat line, that means there's no structure. But if there's a curved line there, it indicates that there's some evidence of chirality, which means it must be folding. So they had gotten these things, but they could not get a crystal structure, no matter how hard they tried. Or NMR, they couldn't get one. So there's helical behavior, but they couldn't see where it was coming from. So we decided to try to do some adamant. Oh, and then you can show that you can denature out with methanol. So something happening in there. And they hypothesized what they thought the helix must look like. So they came up with this idea that, hey, you can form these hydrogen bonds. So just sort of playing around and, trying to see if it's stable using some quantum mechanics, very simply just like single structures. They came up with a structure where you have the hydrogen bonds coming from the amide groups in between the aromatic groups lined up. And they said, we think this looks like this, but this is a complete guess. So we did, hey, brute force approach. Let's just do a lot of atomistic simulations. But what we found is the predicted helix structures unfold rapidly in solution. It's actually chloroform, I should mention that comes up again later. They really just fell apart. And only maybe about 3.5 out of the 7 hydrogen bonds were stable at low temperatures. There was hydrogen bond occurring, but it did not form an ordered structure that repeated, as you would expect with these polymers. So we ran a lot of temperature replica exchange experiments just to see, hey, can we find some other folded state? And we never did. What we eventually did is we were able to run a lot of replica exchange simulations. So we got a full sampling of the configurational ensemble. And what we found is we found some cluster, some of the most populated clusters. You see, they're not populated very much. But if we looked at the ones that had the most hydrogen bonding, what we found is that hydrogen bond formation was anti-cooperative. If you formed one hydrogen bond, it actually made it harder for the next one to bind. So a lot of these structures with hydrogen bonds would have like hydrogen bond, no hydrogen bond, no hydrogen bond. And this provided a lot of the explanation for why they weren't seeing monomers. They could not stabilize a monomer in solution is because simply they did not exist. So this supported experimental observables that POP terphenyl does not form monomeric helices in solution. So they actually did a bit more of experiment and found that the dominant form might be a dimer. They weren't sure, and they could never crystallize a dimer, but that was the hypothesis. So we tried, but it ended up being too expensive to entirely explore the conformational ensemble. With a monomer, all you have to do is worrying about it folding and unfolding. But with dimers, you have to worry about all the different possible ways they could connect. You could imagine some sort of zigzag pattern. But we tried to put it in some of those. We could never stabilize that. So this was a partial success. And then we were able to explain why the proposed structure simply was not stable, because once you form one hydrogen bond, the angle that it was at made it much harder to form the next one. So you could only do alternating hydrogen bonds. But it was too expensive to look at dimers. So that's something to remember. Like, this is partially successful, but they really weren't able to answer the question they really wanted to understand. But they were also interested in design. Hey, we have this pattern, but we could also rearrange. You could still imagine you still have this hydrogen bond that could form a chain along it. But you could, instead of being at para-ortho-para, you could be meta-ortho-para, meta-ortho-meta. There's a lot of different ways that you could design these monomers, right? That's the whole point. We want to have a range of different configurations that would work for monomers. So we started with this one. Let's try the others. Maybe we'll be more successful with these. So we're starting with the meta-ortho-para tetramer. But what we found there is, unlike the original the original one, we actually were getting clusters that were helical. So this is just the tetramer. It's not clear that the tetramer by itself is completely stable. But if you have stability for longer ones, you should see some hints of patterns. And we did indeed. We saw that one of the highest occupied clusters really did have a helical pattern, had repeating hydrogen bonds being formed. And so it looked like this. It was, and you could tell it was helical because if you look at the different torsions, they all occupied the same pattern. So all the monomers occupied the same torsional profile. So it was just a repeating unit throughout. So it was a repeating unit throughout, and we had hydrogen bonds that were stabilizing that unit. So we started with tetramers because we knew it was going to be pretty expensive and slow to start with octamers. The idea is start with the smallest unit we can, see if we see hints of structure, and then see if that structure is stable for larger proteins. I mean, we did have larger folders. We tried for larger folders, and just the timescales did not work. But with the tetramers, we started seeing this. And so we found, we constructed that, and we found that it was at least partly stable for at least several hundred nanoseconds. So this is what a simulation looks like of this structure. You can see it's not entirely, there's doing some weird things. It's starting to fall apart. And so at room temperature, it wasn't stable. This is chloroform, though, so we could make it a lot colder. And as we looked at lower temperatures, this is still above the freezing point of chloroform, we got it to remain stable out to hundreds of nanoseconds. Now, remember, these are force fields, right? If you look at protein force fields, they've been very finely tuned to match experiment. These are sort of off-the-shelf force fields, and so we don't expect them to get the force fields exactly right. But we expect them to be somewhere close. And it turns, although the experimentalists never actually found a structure for this, the student working on it graduated and had to move on, they did see circular dichroism for this terphenyl octamer. So in this case, it agreed with experiment. There should be stable structures, and that's what this hints at. Again, it's not perfect because the force fields themselves are not tuned for all organic chemistry, just mostly for proteins. But the fact that it was stable at relatively low temperatures indicated that we're on the right track. Okay, so we looked at that one. Now, of course, remember these take a couple months of work to try to do, a lot of computational time. So this one appears to be is likely to be stable, and the experiment showed that it was. Let's try some others. Let's try this one next. And so what we found is when we did these simulations, we did get helical clusters coming out with dihedral patterns that were almost consistent. They're a little off in some cases. But here's the crazy thing. There's native context here between the amide groups, but these don't look like normal hydrogen bonds, right? Because the hydrogen, they're not linear, they're stacked. But in chloroform, this actually can be a stable structure between hydrogen bond forming groups. In water, of course, normal hydrogen bonds would completely dominate, and we would want to form those. But in chloroform, there's nowhere else for these to connect. And so you start seeing these stable structures with these very weird parallel hydrogen bonds rather than bonds pointing at each other. And these are actually stable for quite long time scales. If you look at the octamer, you have these structures that are repeating and are stable, with 6 hydrogen bonds, 6 contacts of these polar groups out to hundreds of nanoseconds. Unfortunately, again, the graduate student working on this is graduated, so they never synthesized these. So we're hoping that at some point soon we can resurrect this, because this really does suggest some very interesting possibilities. Again, is this an accident? Is it because our force fields are a little off, so they're stabilizing something incorrect? It's hard to tell, but yeah. So the remaining 2 oligomers had no sign of stable tetramer clusters. So we predicted those would not form stable structures, unlike the MOP and the MOM octamers. So we've This is a very time-consuming process. If you're going to search through all chemistry, you can't take, 6 months to a year to evaluate just 5 different structures. So what can we do? Thinking larger scale now. Let's shelve this direct atomistic simulation approach. What could we do to try to understand general principles about how these oligomers could form? And so our idea is to use coarse-grained models to explore design space and more easily test hypotheses. Designing natural folders such as proteins, as I mentioned, requires knowledge-based force fields or AI to fit a vast amount of data. That data is not available for synthetic foldmers. And as we've seen, atomistic simulations are very expensive. They don't appear to be quite accurate enough for general polymers. They're somewhere in the same range. Like something that's experimentally stable, we can get to stabilize if we go to lower temperatures, but it's not really. We could easily be missing some things. If we try to do something with a high throughput method, we could be missing some of these possibilities. So coarse graining is we replace the description of the residues with a single bead. And there's a lot of ways to do coarse graining. You can imagine doing an atomistic simulation and then averaging out those interactions to create sort of residue-based interactions. But the problem with that is that our atomistic simulations themselves aren't quite good enough. So we prefer something that is much more minimalist. Something we say, okay, we have some interaction parameter involving, say, an entire residue, or maybe just the backbone, one bead representing the backbone, and then one bead representing the side chain. And this is really inspired by a lot of protein minimalist Waddle work by people like Kendall and others, where you take a very simplified description of the system and try to understand general principles from there. And a key thing is, we can, and rather than having our parameters defined by trying to match one very specific experiment, we build our hypotheses into the choice of parameters. And we'll see example, I'll explain what that means as we go along, but we want to design experiments that help us understand how these systems fold by the way we choose the parameters. So the concept is that hypothesis-driven modeling can capture general folding patterns of foldmers. If we have some helical model, maybe we can capture the behavior of many different types of potential helices. And so we can say, let's define the simplest model that captures folding phenomena. And that, we hope, can inform the design choices for more complicated models. If we have some rules that say, hey, we have this very simplified model that has to have these behaviors in order to fold, then that can inform us when we make more complex molecules. Okay, we know what things we have to satisfy. So that's the idea. So eventually what we'd love to do is map our coarse-grained model structures into atomistic structures. So we've built some infrastructure for rapidly simulating and analyzing coarse-grained models of foldmers. And there's really been 2 tracks. One was actually modifications of Rosetta to handle arbitrary coarse-grained environments. So we use the Rosetta protein search framework and the PyRosetta interface. So what it allows us to do is perform rapid searches of structures for low energies. It uses an annealed Monte Carlo process. I'll explain a little more about that. And the idea is that if it's in PyRosetta, that it can transition into more complex structures as well, because Rosetta has some Rosetta has infrastructure to do atomistic searches as well. So this is published a couple years ago. We also developed a framework based around OpenMM that is thermodynamics based. So we use molecular dynamics. We're not just searching for low energy structures. It uses replicate exchange, sampling, and temperature to fold and unfold structures. And because it's using molecular dynamics, we incorporate the entropy as well. And so it allows us to look for properties like cooperativity of folding, stability of folding. How stable is the folded ensemble compared to the unfolded ensemble? And this has been published as well. So Lenny Phobe led the work with CG PyRosetta and Chris Walker with CG OpenMM. So we're starting, like I said, from a very simple minimal model. So, one backbone bead per residue and one sidechain bead per residue. And so we assume harmonic bonds and angles. periodic pseudotorsions to add a propensity for the torsions along the backbone and the backbone side chain to point a certain way, and just Leonard-Jones non-bonded interactions. Leonard-Jones are not great for coarse-grained simulations. They're better for atomistic, but it's the simplest thing to implement. If we're just interested in the minimal model, then any model that gives you both repulsion and attraction will help guide things. And we don't use solvent. That's very expensive. So assume we're averaging out the interactions with the solvent. We're not saying that there's no solvent. We're saying, the potentials that we use include the average effective solvents. So because we're using OpenMM, it has an API that's highly customizable, so we can define user-defined potentials. And I won't get into all of those, but we've tried things like directional potentials or effective solvent models that incorporate the effect of the solvent on the different conformations. So it allows us a lot of different possibilities. And we have a very general coarse grained model builder for both kinds of sampling. So we can construct things like, here's a homopolymer with one backbone, one side chain, but you could imagine 2 beads per backbone and 1 per side chain, or even, cyclic rings inside each monomer. You can define very complex things very simply. So we can use these structural approaches to investigate types of coarse grained models. So again, so we build the course. So Lenny built coarse grained models into Rosetta. And what we do is we start doing Monte Carlo sampling, but then slowly cool down the system. So that's the idea of Monte Carlo minimization. You start sampling the configurations at a high temperature, and you gradually cool that down. So if we look at the average energy, so the red says what the temperature looks like over time, and basically arbitrary units that have to do with relate to the coarse grained attractive energy. And the energy of the system starts out very high as it explores configuration, and then it cools down to near zero, and you get energy minima. So it'll look something like this, right, as it goes through. So we can do this with many, it's relatively quick, just on one core, we can do it with many possible models. And what we get out is folded ensembles. They're not thermodynamic ensembles, right, because they're generated at a range of temperatures, but we can say what sorts of structures come out, and do the low energy structures look like they're folded up? So what we do, once we generate all these configurations, we cluster them and say, hey, are there clusters that have, we generate, and what we look at is, are there clusters that have a very small RMSD between them, like clusters of structures that are very much alike? If they're folded, you should have a cluster where all the structures are very similar. Whereas you should see some distorted structures that are not very similar at all. And so we can look at both the RMSD within the cluster and then say, okay, is there a large RMSD between clusters? If we have a bunch of clusters that are widely spread and are not that different, they're unfolded. But if we have structures that have a very small RMSD, that are very structurally similar and are quite different from other things, that would indicate folded. And we can test our sampling because at least these one polymer, so one side chain, one backbone beads are non-chiral. So if we're sampling well, we should see both the right-hand helix and the left-hand helix. And so this is the sort of output we get out. So looking at this, I've got the cluster RMSD, how far they are from the middle of the cluster, and the average energy. And we can see 2 well-populated right-hand and left-hand helices that have very similar low energies, and then a bunch of structures that are quite dispersed in configuration and spread out. So this is an example of success. This particular set of coarse-grained parameters, angles, bonds, van der Waals, folds, has stable folded structures. So we've successfully identified a model in this case that has stable folded structures. So that's what we're trying to do. And it turns out that as we vary model parameters, we can find a large range of potential helices. So in this case, one case where we can turn like the backbone, tune the backbone angle or the size of the side chain, and we can actually tune how large the helix is. As we go through, you start out with very tight helices. Then as you change that backbone angle, you get very large helices until they're almost essentially rings. So I won't go into all the details there since we're somewhat limited on time, but you can read the paper and see some of the searches we can do. There's one other slide I should have included that shows all the different possible structures you can get. Beta hairpins, just through scanning through parameters, you can find them very quickly. So I'll direct you to the paper if you're a little more interested in that. Okay, so we got a method to search and find low energy folded structures. But that's not the entire story. It's not just about whether the lowest energy structure is stable. We have to know if it folds up in a cooperative way. So we want to move beyond structure to thermodynamics. And so using molecular dynamics, we can capture the Boltzmann-weighted ensemble configurations. Here we're capturing the entropy as well as the energy of the folded state. And we're really interested in switchable materials. That's what Department of Energy was interested in. So we need to be able to observe switching. And what is a good switchable material? And that is you have a small change in external parameter and you get a big change in the behavior. So what that means is we want it to be able to switch over, say, a small range of temperature. We make to have a small temperature range, and it quickly switches to folded and unfolded. So this will allow us to capture phase transitions in temperature, cooperativity, and structural heterogeneity in these models. Does it cooperatively fold? And that will let us know if it's a good switchable material. So these are the sort of simulations we want to do if we had folded helices. This is a good example of something. This is from a replica exchange simulations. The temperature is going up and down, so it folds, folds, unfolds, and refolds over the course of the simulation. That's what we're trying to get out. So this comes to a really important question, and it's an important philosophical and thermodynamic question. And that is, what do you mean by folded? And it turns out our definitions of folded affect the free energy, entropy, and enthalpy of folding. The free energy of folding depends on how you characterize the folded and unfolded states. What is it that means folded? So the free energy difference between two states as a function of temperature is going to be minus kBT log Q1 over Q2. Or you could think of that in other ways as minus kBT log the probability of being in state 1 at that temperature versus the probability of being in state 2 at that temperature. Partition coefficients are just accumulated probabilities. So if you run a simulation, you can find the free energy difference by measuring the ratios of occupancy. But this means that the free energy depends on what you call state I and what you call state J. And if the free energy depends on it, then the entropy and the enthalpy depends on your definitions as well. So this is the sort of results you get out, normalized in units. You get our free energy might look like this. So this is the free energy between the states. So we can see at low temperature, this state I is very stable. There's a melting temperature here, and then above it, the other state is stable. We could also see the entropy change between the two states and the enthalpy change between the two states. You can see that the enthalpy and entropy, they don't remain constant, but they remain relatively constant, which means that the delta G slope remains almost linear, but not quite linear. We'll see that a lot. That a lot of times in college chemistry, in introductory chemistry, we assume that the entropy and the enthalpy are independent of temperature, that they're just constants. And if that's the case, you get a completely straight line for the free energy as a function of temperature. But in reality, there's going to be some change in entropy and enthalpy over temperature. So we see that here. We see, for this is taken from one of our folding coarse grain models, that the entropy is kind of constant, but not entirely. It doesn't change a huge amount. Enthalpy as well remains kind of constant, but not quite. Let me emphasize it again, that nature does not care about our definitions of what's folded or folded. Another way to think about the free energy is that we integrate the Boltzmann factor over all the configurations over some set of configurations. And that's the key. If we're looking at the folded state, we don't change the energy, we change the volume over which that's folded. But what does folded mean? Again, nature doesn't really care. We could think of an example from ligand binding and look at the free energy of ligand binding. You could have experiments that say that the ligand has to be in a specific place to be bound. A competition assay where you compete out a ligand with known binding with a ligand with unknown binding and see what concentration you need. That requires the ligand to be exactly in the place where it displaces the other ligand. But you could also do experiments where it just requires the ligand is bound to the protein somewhere, so it has some energy of interaction, like ITC. And you can show that you get different results of binding depending on how you define binding. So folded, bound, All that nature cares about is whether the molecule has the relevant functionality. If we say, hey, is this enzyme capable of catalysis? It doesn't really correspond, if it can catalyze a reaction, it doesn't really correspond to what the RMSD of the native structure is. All that nature cares about is that when a molecule moves in, the reaction takes place. It could be the part of the protein is completely unfolded, the amino acid is stable. So it's very important when we talk about free energies of folding or what it means to be folded, that really these are our definitions and they might apply or they might not apply. It turns out if there is very few configurations that could be described as in between the states, then the states are relatively independent of how we define them. But there could be other cases where it's very hard, that there really don't exist two separate states. There might be intermediates, or there might not be. Even if there's a stable folded state, it might overlap a lot thermodynamically with a lot of other states. Like at absolute zero, yeah, it's a well-ordered structure, but that structure could fall apart somewhat gradually, and you'll see that it becomes very hard to define what's folded and not folded. So it's a subtle point that I want that comes up again and again, is that nature doesn't care what folded is. It doesn't have a definition of folded. These are all sort of definitions for our convenience. Nature just cares about, does it have the conformational ensembles that let it do what it wants to do? So what we'll do is we'll have to come up with some definitions of folded. So what we do is we determine a native contact fraction. So if there exists a well-defined native state, then we say, okay, those contacts, the backbone pairs, which have the shortest average difference in the native structure, those are our native contacts. And so what we do is we try to figure out native contact pairs and how far apart they can be in order to find a definition that best captures two-state behavior, meaning that it goes from fully folded at low temperatures to fully unfolded at high temperatures. So we find this set of contacts, and that's what we'll use as our definition of folded. And we'll find sometimes it works quite well. You have a very sharp transition between folded and unfolded, and sometimes you don't. Actually, you don't even require sharp transition here. You just require that at low temperature, all the contacts are formed. And at high temperature, you only have contacts that are formed according to random polymer jiggling. So that's what we'll be using as our measure of folded or unfolded. And we'll say when it's at the 50% mark, then that is the line between folded or unfolded. Again, does nature really care about the difference between something that's 0.6 versus 0.4? It's just part of a configuration ensemble. This is our definition that we're applying. Okay, so once we have a workable definition of folded or unfolded, and these equations might start to fall apart if we don't pick good ones. But if there is a distinction between folded and unfolded states, we can start measuring things like stability and cooperativity. So again, what we do is temperature replica exchange MD simulation so that we're able to sample a lot of different configurations. And again, since we're interested in temperature dependent behavior, we're not wasting any CPUs by doing temperature replica exchange. It just allows us to improve the sampling. So we get curves out like this. And what we do is we calculate the heat capacity and the native contact fraction as smooth functions of temperature. So this is an example of a well-folded, something that has very cooperative folding. It starts out having native contacts. That's the cue here. Lots of native contacts. As you heat it up, they disappear. And at a certain temperature, they disappear. And above this temperature, there's very few native contacts. What you generally see in these is because the native contacts provide stability of energy, then you get a change in heat capacity. As it goes from the low energy configurations to the higher energy configurations, you see a spike in the heat capacity. If you think about phase transitions going from solid to liquid, you remember that you have sort of a peak in the heat capacity. If it's a bulk system, then you have essentially an infinite spike in the heat capacity, right? Because you're putting energy in, and it's not raising in temperature because all the energy is going into the phase transition. With phase transitions for sort of not bulk scale objects where we just have, a few dozen atoms, you can't go up to infinite heat capacity, but you do see these big spikes in heat capacity. So that's another thing to look out for. If you have if it's cooperative as temperature changes, you'll have an associated spike in heat capacity at folding. And a lot of times that's what people look for if they're looking for folding proteins, is they watch to see where the heat capacity spikes. That's the most common way to measure melting temperature for a protein. So the key features to look at these are cooperativity. What is the width of this transition region? The width over which the contact goes down, or the heat capacity is wide. And the other is the stability. You want to look at the temperature at the melting point, because that says how stable it is, the temperature at which it transitions between folded to unfolded. So we have a whole workflow for doing this. Chris did a great job in putting this all together. And a lot of it is not just performing the simulations, but analyzing the simulations. Where are they being folded? What are the helix parameters? How many, what's the pitch of the helix? We've mostly been looking at helices, trying to understand the native structure. So this workflow for extracting all this information. And what we find is, hey, you can actually control the cooperativity by doing things like backbone dihedral stiffness. For example, here we have a very simple model. These are all homopolymers. I'm not introducing any sequence specificity. These will curl up just on their own. We say, how stiff is this backbone sort of enforcing a sort of helical behavior? So what you can see, if you have no stiffness at all, it doesn't fold. But once you introduce a little bit of stiffness, it very cooperatively folds. But interestingly, as you make that backbone stiffer, you stabilize the helix, right? Because you're stabilizing this angle that says, hey, wind up in a helix. But you make it much less cooperative. In other words, the shift from folded to unfolded happens at a much wider temperature range. It's a higher temperature, but it's a much wider temperature range. So we can see that stability and cooperativity can actually work against each other. So low dihedral stiffness leads to the most cooperative folding, seen through, again, the heat capacity increases peak height and decreases width as you go to the more cooperative regime. The native contact fraction decreasing transition width at the most cooperative foldomer. So we just have a little bit of bias towards the torsion. And you can, interestingly, it turns out that very small changes can lead to completely different structural ensembles. So for example, here, we're looking at the angle between the backbone and the side chain, that equilibrium angle. And as you, so I know this is the angle along the backbone. And as you tweak that, if it's less than 110 degrees in this model, you have I to I plus 4 helices. You make it just a little bit bigger, all of a sudden it switches into I to I plus 5 helices. So very small changes can stabilize the ensembles. In this case, the I to I plus 4 helix is very cooperative. The I to I plus 5 is not nearly as cooperative. It's still stable at low temperatures in this helix, but it doesn't fold cooperatively. It just kind of slushes into unfolded as you raise the temperature, rather than folding at a very sharp temperature. And talking to experts, they say, this is the sort of change that could potentially triggered by changing protonation state of an monomer substituent, an atomistic model, right? By protonating or deprotonating an aromatic ring, you can change angles by the monomers within themselves by up to 5%, which indicate, it should be possible, if you had the right parameters, to trigger some of these folds, not just by temperature, but by something like changing pH as well. Here's an interesting question: is what secondary structural elements beyond helices and sheets are possible, right? In proteins, we see helices and sheets. Nucleic acids, we see these double helices. What else might be possible? So one interesting structure you see in polymer physics are knots. And so people can, tune a number of different parameters with polymers and get low energy structures that are stably knots. And of course, if you get long enough polymers, you will get knots. And with the right choice of parameters, you can get knots to be the most stable. But the question is, can you get things to stay cooperatively fold into knots? In proteins, you've identified some knot structures as well. So that's what we're interested in. Could we make stable knotted secondary structures as we tune our monomers? And so it turns out that bend equilibrium angles yields a variety of stable homopolymers. So again, there's no sequence specificity yet. Form stable 3D knot structures. So as we tune some of these backbone angles, we get completely different knots. And remember, these knots are completely stable. So this is what it looks like when you simulate it. And so as you change the backbone equilibrium angle, you can get very complicated, completely stable structures. But again, the question is, here's an example of something folding up into a stable knot. It's really quite interesting that, this will happen multiple times. You can fold and unfold these, and the low temperature stable simulation really is this type of trefoil knot, which is pretty crazy that ends up being this stable structure. So if we look at the heat capacity, remember peaks in heat capacity indicate folding. And as we look at some of these, so remember the light blue are these down here, the pink ones are the top row, right? These are changing at different angles. You see pretty high heat capacity peaks. So your first instinct might be to think, we've got cooperative folding. That's fantastic. But it actually masks the complexity of the many states and transitions. So one thing we did is work out sort of what heat capacity actually means in terms of the states. So let's say that we have K states. So the total energy of the system is just going to be the average energy of each state times the fraction, right? That seems pretty straightforward. The total heat capacity is the change in our total energy with respect to temperature. And we can say, oh, well, we got the heat capacity of each state. Can we just add up the heat capacity of each state to get the total energy? And it turns, here I'll define the fraction of the structures in state K as well. And it turns out it's not that simple. There's two contributions to heat capacity. And so this is done for two states before, though I think we've got the first generalization to arbitrary configurational states, is that there's two contributions. There's the heat capacity of each individual state, and there's the heat capacity contribution when you switch from one ensemble to the next. So when you look at the total heat capacity, you have to include both things, the individual state behavior and a term that depends on the difference between the average energy squared and depends on the fraction of both of those states. This is a double sum because it has to do with our state-to-state transitions. And a key thing is, this is valid for any subdivision of conformational space. If you choose a poor subdivision of conformational space, such that the average energies of your states are all the same, you'll just get that the state-to-state transitions will be zero and all the individual behaviors are here. But if the system has a well-defined decomposition with a low energy folded state and higher energy unfolded states, then then you'll get most of the heat capacity in the state-to-state transition. So this is important. Remember, nature doesn't care about our definition. So this formula will hold for any set of definition, any decomposition of what we think the different states are, but it'll only make sense if we choose reasonable states. So here's an example of what this decomposition looks like. So I've got, here's something that folds up well. The individual state contribute. So the gray line is the total heat capacity. And we find that the folded and unfolded states, we see that they actually have roughly the same heat capacity. If we look at the sum of the heat capacity of the two states, it's almost flat. Not perfectly flat, but almost flat. If we look at the state-to-state transition, it is the majority of this peak. So this is an example of a system with well-defined states. Most of the heat capacity peak is due to our state-to-state transition. But if we look at our knots, it turns out that we might have two different folded states that are stable at different temperatures, but there's also a globule state. That's a state that's highly compact, but doesn't really have any fixed folding behavior. It's just sort of all jumbled up together. And the coil would be an unfolded state. There's different states. And if you look at the transition contributions, so this gets the light gray line is the total. Our transition between the heat capacity of these individual states is not really constant. It has big peaks. Especially this globule state has a really high peak. And if we look at the transitions, the highest transition is actually coil to globule, right? The things we want, the folding into well-defined stable states, are these two lighter lines, and they're very small. So what we're seeing, even though we have something that looks like it's a highly cooperative transition, it's a bunch of different transitions together. So these are stable folded states, but they're not very cooperative. At low temperature, they dominate, but you just sort of get a mess of all these different states together at intermediate temperatures. This would not be a well-switchable material. You'd have a hard time building up larger polymers out of these sorts of secondary structures. So one thing we can discover, these are all polymers with just backbones. If we had side chains, we can get significantly more cooperativity. So what I'll emphasize is looking at the transition. Now, this blue line is pointing towards this transition from the coil to it should be from globule to, let's see, no, we want coil to folded state 1. Is that not line? I think this got cut off a little bit. Oh, so turns out that this line here is the transition from state 1 to, it's a problem with putting and saying that's too complex, too many data points, is that we have a lot more higher peaks between the folded state, from folded state 1 to the totally unfolded. Oh, I'm sorry, yeah. So state 1 globule. So here our transition, no, that isn't. This is the state 1 globule. The state 1 globule transition is nearly as cooperative as globule coil. So we're getting a point where we get a cooperative transition out of a well-defined state into an unfolded state. So obviously there's still a lot more work to go, but we start seeing these transition peaks. Here, all of the folded state transition peaks are down here, but now our folded state transition peaks are starting to be a significantly larger component. There's still a lot to, more to go on this, but remember, there's no sequence specificity whatsoever. These are states that, this is sort of the transition, cooperative transition bunk here. This is from coil to globule. This is from globule to chain. And so we're getting somewhat cooperative knotting, some of the details of this. And this is really sort of the first knotted homopolymer with side chains seen in the literature. So this is what it looks like folded up. So this, unfortunately, Chris ended up having to move on to more project, a different position before we could go further than this. But eventually we want to try to add some sequence specificity in there and get things that fold up very cooperatively into the space. Remember, this is totally without sequence specificity at all. This is just packing. So the last thing I want to talk about is really, what does it mean to quantify cooperativity? We say, hey, the width of this, but there's really a few different ways to talk about it. The width of the heat capacity curve might be one. The slope of fraction of folded state at halfway point, right? You want that fraction of folded state to be going down as fast as possible. Maybe the slope of the change in free energy when the free energy is 0, because that's saying it's transitioning between folded to unfolded states very quickly. But the good thing is, it turns out that all of them are the same up to a constant. All of these things you can define as just the difference between the energy of the folded state minus the unfolded state divided by the temperature at the melting point squared. All of them are up to a constant, whether this is 4 or 2 or square root of 2, that will depend on what you're choosing, but all of them are the same. So that starts to point to how we can really define what makes things cooperative. Equivalently, since delta H is T delta S at transition, it also can be related to the difference in the entropy of the folded and unfolded states divided by the melting temperature. But one thing that's a little annoying about these is that all these measures of cooperativity have units inverse temperature, or equivalently, you can think about them inverse energy. What that says is that at a higher melting point, it's harder and harder for a transition to be cooperative. And that's because at higher temperatures, all states become more evenly probable. So it blurs the transitions between higher and lower energy states. So what we've come up with is defining a cooperativity measure with respect to T over Tm. So this intrinsic cooperativity turns out is just proportional to the change in entropy. What the physical meaning is that the most cooperative transitions have the largest entropy differences between folded and unfolded states at melting. So this is sort of like the key finding for all of this, is that you can make things, the way to maximize cooperativity is that the difference in entropy at the melting point is the largest as possible. So it makes it clear what's going on with cooperative transition. So it allows us to decouple the stability and cooperativity. We got 3 analytical models here. And if you look at this, they all have different temperatures. They'll have different stabilities. And so it's sort of hard to compare how these work. But if we look at intrinsic, if we look at the fraction folded as a function of T over Tm, so we sort of normalize for the stability, it becomes much clearer which things transition steeply and which things do not. But even understanding what makes something cooperative still leaves us with a design challenge. If the entropy in the folded and the unfolded states were constant, then we could just say, hey, I want to define something that has a very low that has very low entropy of the folded state, and maximize entropy in the unfolded state and be done. But it turns out that the entropies are themselves temperature dependent. So here I've got a decomposition of entropy of the total, and these are some analytical models. The total entropy, so they should be very simple, right? The total entropy, the folded state entropy, the unfolded state entropy, and the delta S. And of course, the folded state entropy is always lower than the unfolded state entropy, right? That's what it means to be a folded state. It's a low entropy state. But we can see that the entropy of the folded state still increases with highest temperature, as does the entropy of the unfolded state, which makes sense. You get more motion. So you can't just say, I want to define a low entropy state, because you never really know exactly what the temperature dependence is. Here's one example. It seems relatively straightforward. But here, if we look at that, here the delta S is relatively constant, but here the delta S changes quite a lot. And so it's not necessarily as hard as easy as we might think to design this entropy difference between folded and unfolded states. Okay, so that's sort of the best rule we've come up so far, but we still got a long way. One system we're testing right now to show the effect of entropic difference unfolding is this sort of sidechain with a three-particle a folder with a three-particle backbone. And in this case, we can connect these three particles in a lot of different ways. And we can keep the energy of the native state the same, because the energy is essentially entirely the energy of these Lennard-Jones interactions. I mean, there's angle energies as well, but those will be the same in bounded and the folded and unfolded state. And we don't have results right now, but we can adjust the amount of entropy while keeping the same native state. So what do we want to do in the future? Like I said, this is sort of towards being able to do the design. This is what we found so far. There's still a lot of ways to go. Can we identify all atom structures that correspond to our coarse grain foldmers, or are the details too important that you really can't jump directly from coarse grain to all atom? Can we connect identification of low energy folded state design, like we've done with Rosetta, with the thermodynamic of cooperativity? Because that we require a lot more simulations to get the cooperativity done. Can we find ways to sort of guess what the stability will be based on low energy folded states? How do we do a higher throughput screening of atomistic structures, right? We try to do some of this, but is there a way we can connect the coarse grain and the all atom simulations to do higher throughput screens? So summary of what we looked at so far. So we can investigate these atomistic foldmers. It's very difficult. We have a good framework for exploring hypotheses about coarse grain foldmers, and we can decompose the state thermodynamics in a formal way that gives us a much better sense of what's going on. These CG knots can probably be folded cooperatively, so I think there's a lot of interesting possibilities for knotted structures in the future. And cooperativity, we found, is determined by the entropy difference between states at melting. That's one signal that if you can maximize that, you will maximize cooperativity by definition. But there's still a lot of work towards elaboration design principles. I mean, when you think about it, how many people have investigated how to design proteins over the years? So being able to design everything besides proteins is obviously going to take a lot more work and effort. And I'd be happy to talk to people if they were interested in exploring some of these ideas more. So thanks so much for your attention, and a little bit long, but hopefully we have a little time for questions. So thanks so much.